On November 7th, 1940, a suspension bridge over Puget Sound began moving in a way no bridge ever should. The roadway rose, fell, and then twisted violently as if the steel itself had turned flexible. Within minutes, the Tacoma Narrows Bridge was tearing itself apart in the wind. Just 4 months earlier, Galloping Gertie had opened as a symbol of modern engineering. Its center span stretched 2,800 feet, making it the third longest suspension span in the world. But the bridge was also unusually light, narrow, and shallow for something that large. Engineer Clark Eldridge's earlier concept used deep stiffening trusses beneath the roadway. The final design, led by Leon Moisseff, replaced them with solid plate girders only 8 feet deep. The result was cheaper, slimmer, and far more flexible. That flexibility showed itself before the bridge even opened. As workers finished the deck in May 1940, they watched the roadway move up and down in wind. Construction crews nicknamed it Galloping Gertie. The movement was obvious enough that engineers immediately began looking for a fix. They tried hydraulic buffers at the towers, hoping to damp the motion. They added tie-down cables to restrain the side spans. Professor F.B. Farquharson began wind tunnel studies using scale models. The bridge kept moving anyway, especially through the center span. The dangerous part was not simply that the bridge could bounce. Its proportions left it with very little resistance to twisting. The center span was 2,800 feet long, while the deck was only 39 feet wide. The shallow solid girders also blocked the wind instead of letting it pass through. When wind hits a flexible structure, the structure changes the airflow, and that changed airflow can push back on the structure. On Tacoma Narrows, the deck behaved partly like an airfoil. Lift, drag, vortex shedding, and the bridge's own motion began interacting with one another. This is why the famous schoolbook explanation of simple resonance misses the real story. The destructive motion was aeroelastic. Once the bridge began twisting, the changing angle of the deck changed the aerodynamic forces acting on it. The motion could feed itself instead of dying out. The morning of November 7th brought strong southwest winds. At 7:30, wind near the bridge measured about 38 miles per hour. Later, engineers measured around 42 near the east end. The bridge began its familiar vertical waves, sometimes rising and falling several feet. Shortly after 10 in the morning, the motion changed. A cable band at mid-span on the north main cable slipped, helping divide the cable into unequal sections. The deck shifted from mostly vertical movement into torsional oscillation, with one side rising as the other side fell. Now the bridge was absorbing more energy from the wind with every twist. The deck rotated, the airflow changed, the aerodynamic force reinforced the rotation, and the cycle repeated. This self-excited instability is called torsional flutter. Once it grew large enough, the bridge could no longer survive it. People near the bridge watched the roadway rotate at terrifying angles. Reporter Leonard Coatsworth abandoned his car on the span and crawled back toward safety. His daughter's dog, Tubby, remained inside. Attempts to rescue the frightened dog failed as the bridge's movement became too violent. Around 11 in the morning, the structure began breaking apart. Concrete sections dropped into Puget Sound. Steel girders buckled and twisted. Suspender cables snapped. Successive portions of the center span fell away until the heart of the bridge disappeared into the water below. By about 11:10, Galloping Gertie was gone. Remarkably, no people were killed. Tubby was the disaster's only victim. The bridge itself had survived only 4 months, leaving engineers with one of the most dramatic failures ever captured on film. Investigators concluded that the bridge's extreme flexibility and its solid plate girder deck were central to the failure. The disaster exposed how poorly engineers of the era understood aerodynamic behavior in very long suspension bridges. Wind could not be treated as only a static sideways force. The replacement bridge opened in 1950 with a much stiffer design, including deep open trusses that allowed air to pass through the deck structure. Tacoma Narrows changed bridge engineering worldwide. The warning had been visible from the beginning. If a structure moves in a way you do not understand, that movement is part of the design problem. This is collapse logic.